And what if I told you that the constant, unwavering flow of time you experience every single moment is a profound illusion? That the sharp line between past, present, and future isn't as solid as it seems? The clock on your wall, the calendar on your desk, they measure something. But modern physics tells us it might not be the fundamental reality we've always taken for granted. The journey to understand time has shattered our most basic intuitions about the universe. It's a story of revolutionary ideas, mind-bending experiments, and a quest that continues to push the very limits of science. If you want to explore the biggest questions of the cosmos, make sure you subscribe and hit that notification bell because we are going deep. For centuries, our understanding was simple, shaped by the genius of Isaac Newton. He envisioned time as a cosmic clock, ticking at the same rate for everyone, everywhere. It was absolute, a rigid stage upon which the drama of the universe unfolded. One event happened at time t1, causing another at time t2, and that sequence was the same for every observer, no arguments. This intuitive idea, it makes sense and it works perfectly for our everyday world. But at the dawn of the 20th century, a patent clerk named Albert Einstein shattered this universal clock forever. Einstein's revolution began with two simple yet powerful ideas. The laws of physics are the same for all observers in uniform motion, and the speed of light in a vacuum is a universal constant. From these postulates flowed a shocking conclusion: time is not absolute. It's relative. This is the core of his theory of special relativity. It predicts a bizarre phenomenon called time dilation. The faster you move through space, the slower you move through time relative to a stationary observer. This isn't just a theory, it's a proven fact. Classic evidence comes from particles called muons. These are created high in our atmosphere and travel towards the ground at near light speed. They have a very short lifespan, so short that, classically, they shouldn't have enough time to reach the surface before decaying. Yet, we detect them in large numbers. Why? Because from our perspective on Earth, their internal clocks are ticking much slower, allowing them to survive the long journey. This was confirmed by the Rossi-Hall experiment in 1941, which provided direct evidence that moving clocks run slower. But Einstein wasn't finished. With his theory of general relativity, he wove time and space into a single fabric, space-time. And he showed that this fabric isn't flat, it's warped and curved by mass and energy. We perceive this curvature as gravity. This means that gravity doesn't just pull on objects, it literally warps time. The stronger the gravity, the slower time flows. This is gravitational time dilation. Again, this isn't speculation. It was spectacularly confirmed by the Halfel-Keating experiment in 1971. Scientists flew incredibly precise atomic clocks on commercial airliners around the world and compared them to identical clocks back on the ground. The flying clocks experienced weaker gravity at altitude and gained time, while their speed also affected the result. The results perfectly matched the predictions of both theories of relativity. This effect is so real that our GPS systems have to constantly correct for it. Without accounting for time dilation, your GPS would become inaccurate by several miles every single day. So, time is relative. It's a stretchy, deformable fabric. A strange yet well-established scientific fact. But as we transition from the cosmic scale of gravity to the bizarre realm of quantum mechanics, the nature of time becomes even more mysterious and challenging. At its core, quantum mechanics is probabilistic. It describes the world in terms of wave functions, which represent a cloud of possibilities. Only when we make a measurement does this cloud of possibilities collapse into a single, definite reality. This collapse introduces a fundamental randomness and a break in the smooth, deterministic flow of time. Then there are phenomena that seem to defy linear causality altogether, like quantum entanglement. Einstein famously called it spooky action at a distance. D2 entangled particles can become linked in such a way that measuring one instantaneously affects the other, no matter how far apart they are. This instantaneous connection seems to mock the cosmic speed limit imposed by light. It challenges our notion of separate events and suggests a deeper, non-local reality. The delayed choice quantum eraser experiment is perhaps the most mind-bending experiment of them all. It builds on the double-slit experiment, but with an added twist. A photon is sent towards a screen with two slits. Its entangled twin travels along a different path towards a set of special detectors. If we measure the photon in a way that reveals which slit its twin went through, the twin will behave like a particle and not create an interference pattern on the screen. The choice of how to measure the photon can be made after the twin photon has already hit the screen. If we choose to erase the path information, the interference pattern, typical of a wave, magically reappears from the already collected data. This demonstrates the deeply strange and non-local nature of quantum reality. Simply put, it suggests that a choice made on one particle in the present can appear to retroactively change what happened to its entangled partner in the past. But it strongly demonstrates that our classical ideas of before and after are not well defined at the quantum level. This is where we transition from established science to the realm of speculation. Physicists are trying to unite Einstein's gravity with quantum mechanics into a theory of everything. The two leading candidates, string theory and loop quantum gravity, treat time in even more radical ways. String theory suggests that the universe has extra, hidden dimensions, and that what we perceive as space-time might be an emergent property of the vibrations of tiny, fundamental strings. At the most fundamental level, time as we know it might not exist at all. Loop quantum gravity proposes that space-time itself is made of discrete, indivisible quanta, or loops. If this is true, then time doesn't flow continuously. It jumps in incredibly tiny, discrete steps. In this framework, defining the flow of time becomes a huge challenge known as the problem of time. An even more speculative but fascinating idea is that time itself might be an emergent property of quantum entanglement. In this view, the universe is a static, timeless web of quantum correlations, and the flow of time we experience is just a macroscopic illusion arising from these connections. So what does all this mean for our perception of reality? Science shows that our intuitive sense of a universal, absolute now is wrong. Our brains construct our sense of time, which may not be a direct reflection of physical reality. From Newton's absolute clock, to Einstein's dynamic space-time, and now to the quantum realm where time itself might dissolve, our understanding has been completely transformed. The solid ground of a universal now has been replaced by a fluid, observer-dependent reality. Frontier theories suggest that it might be an emergent illusion, a shadow cast by a deeper, timeless reality. Perhaps understanding the true nature of time is the final key needed to unlock a complete theory of everything, a final set of laws governing the entire cosmos. The only thing we know for certain is that the simple tick-tock of a clock hides one of the deepest, most beautiful, and ongoing mysteries in all of science. If you enjoyed this journey to the edges of reality, hit that subscribe button and join us again as we explore the cosmos. Thanks for watching.